Hello and welcome to this first webinar of the new year. We are beginning the year with this webinar on error handling in Dyalog, and this is but the first part of a small series on error handling. What we're going to go through today is the very basics of dealing with errors. So if you are an experienced APLer, you might not gain so much from this. However, in upcoming webinars in the series, we're going to go into more advanced techniques, and this is just the groundwork for that. So what we are going to go over today, we are going to look at what's called an event, and specifically there are two types of such events in Dyalog APL. There are errors and there are interrupts. However, for what we're going to deal with here in the beginning, we're going to limit ourselves just to errors. Associated with such events are event numbers and event messages. Because we're only dealing with errors, we are going to forget the official terms and just call them error numbers and error messages because it's much easier to remember. Once it's clear what they are, then we're going to look at trapping an error. And today we're going to look at how to do so in the neatest way in a tradfn and the neatest way of doing so in a dfn. There's actually a third method that is applicable everywhere, and it has some abilities that the neater methods don't have, but it's rather advanced, and we're going to go over this in a later webinar. So what is it that we mean by an error? It means that the normal flow of execution of code is interrupted because the interpreter simply cannot keep doing what it was doing before. And special action has to be taken. Here's an example. We are indexing into a vector, asking for the element in position 4. But there is no element in position 4. There's nothing here that the interpreter can do to continue. Similarly, if we are trying to add two vectors and they have different length, then as we go through the elements and we reach the third element, we have nothing to pair it up with. And there's nothing the interpreter can do to fix this. And so too, if we were to try to perform this division, then we hit a division by 0 error, and since the result here is undefined, then APL cannot continue. Okay, so that's what constitutes an error. An error number is how we talk about a specific error. Some languages have error objects that can be passed around. However, as with many things in APL, we have very few data types, and instead we use those data types, basic data types, to represent all forms of information. And so, errors in APL are identified by an error number, which is just like any other normal number. It's just that in the context of errors, these numbers represent a specific type of error, but they are just normal numbers. And for that, we have a system function called quad_en, error number. And we can see if we go back to our example where we're trying to index to get an element that doesn't exist, we have APL report the error, and immediately after that, if we execute quad_en, then we get the result 3. And this is a normal number 3. It just indicates the index error. Okay, if we try this again with the two vectors that we're adding together, which makes APL report an error with the length, then quad_en is going to give 5. And if we start over and try it with the division, then we can see that quad_en gives us 11. So remember those, because there will be a quiz at the end of the show. Right, it's kind of hard to remember those and deal with those. So for humans, we have something called an error message, and we have a system function, quad_em error message, which can take an error number and report back what the corresponding error message is. So going back to our example, after we get this quad_en, which returns 3, we now apply quad_em to that 3, and that gives us index error, which is a normal character vector. And that index error, of course, matches the text that the APL showed us when we first hit the error. And it's called an index error because the error happened when we were indexing. And if we go to our addition of two vectors, try quad_em on the 5, we get a length error. And that's of course because the lengths don't match. And if we try with the division, we can get the text domain error. And that's because 0 is not in the domain of the right argument for division. Okay, so now we know how we can identify our errors after they have happened. How about continuing execution even though we have hit an error? And for that, we need an error trap. So there are these 3 methods of trapping errors. There's a control structure for threadfence, which is :trap. There's something called an error guard in defense, which is denoted by 2 consecutive colons. And then there's the more advanced method, which is a variable you set up, quad_trap, that gives instructions to the interpreter on what to do when an error happens. But we're not going to go through that today. So for the first one, quad_trap, it's :trap. Now, if you've dealt with threadfence, then you know how the control structures work. So here, where we pass in an argument, and we're using that to determine which branch, so to say, we are going through in the function. And then at the end of the structure, we continue. Now, trapping works very similarly to this. Instead of if, we have :trap. And if you want, you can put :end trap at the end. And then instead of just a simple result, we're trying to try some expression that may fail. And now when we run it with a 1, then everything just works, which means the else branch was not visited at all. But if you try it with a 0, that's when we hit a domain error. And the domain error, we know from before, is error 11. But we have set up a trap for error 11. And therefore, we go down to the else branch, and then execution continues. What happens if we give it a 2-element vector? Then we get the length error. So we can see that the length error, which has a different error number, was not trapped, because the trap is specific to error number 11. But we can add another number to the trap statement. And now it's going to trap both types of errors. If we go back for a moment to our if statement, there's actually a more advanced form of if, because if can only choose in a true-false case. But what if there are more cases? Then we have the select structure, which is also called switch or case in other languages. And there we take a specific value, and then we jump down to the branch that corresponds to that value. And we can do the same thing with the trap. So here we are trapping both the 11 and 5, but we are taking appropriate action for each one of them separately. There's also a special number, number 0, which is not really the number of any particular error. Instead, that means all the numbers. So here we trap all errors, no matter what happened. And that's often bad practice to do if you're deep inside some program, because there might be some type of error then that you don't really detect appropriately and take the appropriate action for, because you haven't anticipated it. And you should really see that during development. However, if you create a full application, then you probably want to wrap the entire top level function in a :trap 0. And then if any error happens which you haven't expected, then you might want to pop up some kind of message to the user saying that an unexpected error happened and an email has been sent to the developers, and then shut down the system, or maybe restart it. And similarly to with the select statements, then we can also add an else here. So here we are trapping all errors, taking specific action for error number 11 and 5, and letting all other actions take a fallback action. All other errors go to a fallback action. So if we try this, we're trying to apply it on something that gives us a length error or a domain error, and it gives us the expected results. And here we are using a matrix, so we're trying to pair up a matrix with a vector, and they don't match at all. So we go to the fallback, the else clause, and that's because it's a rank error, and rank errors have error number 4, which is not one of the ones we took specific action for. Now when you're writing your programs like this, if you're dealing with a lot of different errors, it may be unpleasant to deal with the error numbers. Now for that, it would be nice if you could use text, human readable text, to specify which errors you're trapping, rather than using those numbers. So in effect, what you would want is running quadem but in reverse. And we don't have a built-in functionality for that. However, there are things you can do. And I've here collected 3 approaches that I think are of interest for dealing with this problem. And you can make variations of your own on them. There are more than one way to do each thing. So if you're just dealing with a few different types of errors, and they're basically all happening in the same place, then you could set up simple variables with names corresponding to those errors. And then you can go ahead and use those variables instead of the raw numbers. And that's of course because the error numbers are just plain numbers. The second approach, if you want to deal with a lot of different types of errors, it may be unwieldy to have floating around variables for every single type of error. Instead, you could create a namespace that contains all these variables. So here we create a namespace called error, and we run quadem, which works on vectors on all the numbers. And then we do a little bit of text replacement just to make it easier to use. So if it has a trailing error, like we had domain error, rank error, length error, we can skip that. And then because we are creating names in a namespace, we can't have strange characters either. So anything that's not a word character, any sequence of non-word characters, like spaces and dashes that could occur, we replace them with a single underscore. And here we are creating all these names inside the namespace. So we're creating a name list and all the numbers, making it all into a flat character vector so that we can execute it inside this namespace. And this allows us to write colon trap followed by error dot and then the name of the error that you want, which I think is pretty neat. And of course this works like with any other namespace and dudding and expressions, so we can do multiple errors like this. And finally, we can actually create kind of the inverse function of quadem. So here I've defined that as a train. It's quite simple. It does an inclusive simple so that we can handle even a single error message. And it looks it up in this pre-computed array, which is similar to what we did before. Quadem iota 99, that's all the messages, and then we just remove the trailing word error. And this allows us to write colon trap, and then error, which is the name of our function, and then any one or more of these error names. So if you want, you can modify these to your liking. You might, for example, want to use lowercase or some other shortening of them. Okay, now we're moving on to how to catch errors in defense. It works entirely different than the structure we had in tradfens. You're probably familiar with guards if you've used defense at all, where we have a condition, a colon, and then a result expression, where if the condition holds, the defense will immediately terminate with the result of the result expression as its result, if any. And error guards work kind of similarly. So here's a simple defense, and it does some indexing. Of course, if we run it with a 4, we get the index error, just like we did with the tradfen. The way the error guard works is instead of having a condition, like in a normal guard, which has to evaluate to a 1 or a 0, it takes a single or a list of error numbers, which are just the same as what we were dealing with in the tradfens before, on the left side of the double colon, and then an expression, the result of which becomes the immediate result of the function if such an error is seen after this error guard has been set up. So you can defer setting up this error guard until you reach the point where you want to check for this error, or catch this kind of error, and take special action. That's also why guard is a good name for it, because it's as if at this point, we set up this error guard to watch out for any error that might happen below it. So if you run this, then we can see that we caught the error and returned the expression. And just like we call on trap, we could have two numbers, and this lets us catch both this domain error, where we're trying to index with a character, which can't work, and this, where we're actually getting a length error. And just like with colon trap, we can use a 0, which means catch all errors. We can also set up consecutive error guards, and they all apply from then and up. So when an error happens, what the interpreter does is it looks up and finds the closest error guard which is able to catch this error, if there is any. And these error guards, they also apply to any functions that our function can call. So if you call something that might error, then you can set up a guard and that will catch it. Now what you can't do is continue execution, because remember, the error guard, when an error happens, causes the function to immediately terminate with that result. So this code is faulty. What it's trying to do is assign something to Z here, and then expecting continuation at the bottom. But that won't work, because as soon as the error happens, the function terminates, and because the last statement executed before termination is an assignment, the function will also be shy, which is of course not at all what we meant. Instead, what you have to do is take the whole code and wrap it in an inner function, such that the inner function returns the result, and that, so to say, collects back the various now diverged flows into a single path again. So here we are passing in the argument, and then we either finish on this line down here with a proper result, or one of the guards kicks in and we return one of these results, and then that all gets fed into Z. And finally we can use Z down here. However, I would recommend against writing your code like this, because it makes the flow, the order in which lines are executed, rather involved. It's much better to give this inner function a name, and then we don't even need the variable anymore, because we can just use it straight down here in the final line. So we don't need any variables. It's a quite functional approach to things. However, if you do a lot of this in defense, then that means you don't have a very straightforward path through your function. And with such a branched out flow, you may just be better off using a threadfin, where the flow is clearer to spot using the keywords. Okay, so to summarize all of this from today, we've got a structure in threadfins, colon trap, and we've got the error guard in defense with the colon colon. We can identify the last error with a quad en and get the message for it with quad em. And if you know which error, the name of an error you want to catch, but you can't remember the number for it, then I recommend going to applecart.info. And you can either in the URL put in what you're looking for, or you can use the interface there. And if you just write colon colon and the message that you want, and it doesn't even have to be uppercase, then you should get a result that includes the number. There are some more details to these things as well, but if you type them into the interpreter and press F1, then you can get the full documentation for those at any time. And that's all for today. The webinar schedule for this year is a bit different than what we're doing during last year. This year, Dyalog is going back to having a webinar about once a month, precisely every 4 weeks, while the British APL Association are continuing with their webinars, which are open sessions, which just means anybody can bring anything unless otherwise stated. And they are continuing every second week. So that's why we're doing a 4-week interval so that we never clash with each other. All of these on Thursdays. So every other, should we say, Dyalog slot Thursday is being skipped. In 4 weeks, we'll be back with Richard Park doing Boolean scans and reductions, which are efficient methods of doing things in APL. And 4 weeks after that, I'll be back with the second part of this series on error handling, and we'll go into some more advanced features of the error handling system. You can find more information about the British APL Association webinars on their website, including how to enter them. They are meetings on Zoom, and you'll need the code that it says there. Thank you so much for watching today, and if you have any questions, then feel free to ask them in chat. I'll remain here for a little bit to see if there are any questions coming in. Okay, it doesn't look like it, so thank you very much for today.